we need to have one. But in any case, I'm really happy to introduce our guest speaker today, Yifan Wang. I was lucky to have her as my mentor during the summer at Adobe Research. But many of you might have seen some of her works. I feel like I got to know most early work that I know of her is neural cages. Uh, and I think differential surface splatting almost acts like a precursor to what we do now everywhere, like Gaussian splatting. And lately, she has been working on Gaussian reconstruction models and rig anything, and I'm sure she has like a lot more exciting research to share today. Just quickly, she did her PhD with the one and only Olga at ETH, and then she was at Stanford for doing her postdoc with Gordon Weinstein, and now she's at Adobe Research. So I'll let her take the stage now. Yep.
Thank you, Aditya. First of all, I want to really thank you all for this invite. It's been a long time since I gave a talk outside of product manager, etc., and or small teams working on this one specific item that everyone knows the context. So this is awesome. I want to do more of this. Second, I want to apologize in advance because I'm in the middle of a move. So I put the slides rather quickly. So the remaining time, I really invite, I'm going to go over the slides slowly, and thanks for the delay at the beginning, so it doesn't look like super short. Like every step along the way, I invite questions and discussions. We can also have a lengthier discussion in the end. Because the title is somewhat, so it's a I've been, having existential crisis since 2 years ago. Um, where are we going, right, as 3D researchers? Especially, I remember, I think 2 years ago at CDPR, I gave a talk exactly about why I think it's important to inject 3D priors. And now I look at the talk, I want to dig a hole. um, they are, I think it has just proven so repeatedly that actually the key ingredients seem to be data, like getting data, how your smart engineering of your model sometimes can be in the end brittle, and how, just by having data, in the end your solution might be general and some magic can happen. So like here in this talk, I just want to share some new thoughts about what 3D is serving in the context of GenAI. And so yeah, with that, I'll just go in there. So first, like Aditya said, I did my PhD in a very geometry-centric lab. And the PhD title has geometry in there, and it was, I think, like the early movement to how to incorporate deep learning into geometry processing to graphics. And pretty much the recipe is that you take A and B, right? You take what has been there in computer graphics and take a neural network and you combine it to do some tasks that was done before, but you do it faster and more generalized. And this, I think, applies to neural cage. It applies to work on a displacement map using neural representation. So I would say the recipe has been tried, and I don't think it applies to this day. But right now, I am working at Adobe, and again, I see just magic happens from diffusion models trained on images and videos. And they produce stunning visual result, especially for maybe, I guess, at Adobe, people really care about the pixels. There is nothing you can beat just with the diffusion model. And there's so much priors, like lighting is somehow already embedded just from the pre-training. And then how I see 3D is placed is in very interesting places. First of all, as I'll show later on, it's actually a way to have an intermediate playground, a play-doh that is faster, reactive, and also more, I say it gives you explicit control, but also because we have so many tools already developed for 3D, it's real time. Like you can move something, rotate something, and change the light, and it gives you basically a real-time feedback. It may not be, so given other elements in the scene, the background, etc., it may not be the most pixel perfect thing, but it's potentially a much user-friendly feedback loop. And then we'll also talk about how 3D can be provided as a data source to generate more, let's say, generate more consistency in the training data and potentially kind of inject control in an implicit way. So the focus in my, I would say, since I joined Adobe is more or less how do I bring the hardcore 3D, how do I hide 3D in the creative tools in such a way that it's still useful, that users will never know that, oh, I'm rotating it something this fast is because there's a 3D behind it. But 3D is such a scary word for many people. How do we hide it but still make use of it? That's a very lengthy intro. And here's the kicker, right? So there's an elephant in the room, as I already said it. The generative videos are here. They are getting better. I think one day you will get there. And so in a sense, pixels are being solved. And I think people are focusing rather on efficiency right now on the pixel level. So like I already answered, the big question is our explicit 3D modeling still necessary? And here I basically want to show how, I basically tried Sora at some point, and this should be me, right? This is, and you see my face right now, and you will see how this video just slowly gravitated towards someone else, which is not me. But oops, it's a little loud. Do you hear it, by the way, when I play this? Do you hear the sound?
Yeah, we can hear it.
Okay. Let me
Just a second while I get this unlocked. Ready?
Okay.
Stay with me, good boy.
And then
Feels nice
this
out
is
today, huh?
obviously no longer me. And in between, you also saw like some weird actions happening, and it's great. But I think the problem is that everything being compressed in the latent code and some latent representation, it does have the issue of identity shifts. People are trying to fix that. But still, in my opinion, how we fix that probably needs some more explicit, either explicit memory holder, or some, in our case, actually, some if say I encoded my face, and there is like the animation sequence, if everything is more like controllable or 3D relatable, you might be able to actually like go back and look for the same identity, and potentially you might be able to like change the poses, not just by typing, right? Not just by, sometimes the user are frustrated, like I like this image, but I want to turn it slightly or turn the angle slightly. This just by typing it how slightly, right? How it will be so much easier if you have actually a 3D scene and then you change, manipulate. And so yeah, with that, I want to actually make so the thesis of this talk is I want to say 3D is sometimes invisible backbone. And what currently our user workflow is that user has certain content, and in that content, user has certain intent. Let's say I want to generate such a video or such an image, or I want to put a certain new content in my image. And then we have a 3D generation. And with that, the 3D generation, actually the structure and geometry, as well as the whole lighting itself, act as certain constraint. And then you, under this constraint, you can manipulate it and view it. And then finally, at the rendering time, you can apply your diffusion model conditioned on these 3D to make sure that a pixel looks perfect. So like I said, there's like, if you have the 3D, because it's like all these things are controllable, and it should be, all these geometry, lighting, and parallax should be guaranteed. And then what's scary in the workflow is that 3D editing and manipulation is hard, but hopefully the user actually never needs to know. It never needs to know that there is a 3D thing behind it. And so the case study here is that I want to show two projects. One is a project Turnstile, and it's a group effort presented at Adobe Max, and I will kind of show you what is the workflow. And then SplatPainter, which is a paper we are putting on archive. We put it yesterday, so it might be out today, and if not, then later today. So let's first take a look at Project Turnstile, and this is Zhiqing presenting it at Max this year.
You might recognize our last presenter from last year, where you showed off Turntable, which is now in Illustrator Beta.
I don't see
okay.
that.
Yes. Rockstar. Well, this year has a news surprise. Please welcome
fast forward
with Project Turnstile. Welcome.
Oh, it's very slow.
Thank you.
I do want to
thank you,
fast
everyone.
forward it.
Hi, Jessica.
But
Okay, so it's about Halloween, so I want to design a scene with a Halloween scene. I have spent a long time working on this asset, and I want to put my asset into this.
Oh yeah, this is
So
important. So you see there is a scene, right? A 2D image, and then there's an image, cropped image of this tombstone. And so usually you drag and drop to this canvas. And then
it seems the viewpoint of my asset doesn't quite match with the background, and I wish I could turn that asset to the right, but how do I do that?
So yeah, now is the kicker. So how, like, what we want to do, what the user sometimes want to do, is that they want to turn this some object slightly.
You might already notice the 3D rotate button down here. So let me just click it and introduce Project Turnstile, which gives you complete control over the viewpoint of an image asset. After clicking the 3D rotate button, I'll get a 3D shift.
So what happens here, that is something that rotates very fast in real time. You can, so the user then can just place it as the way they want. And the real time here is an issue. You don't want it to be, oh, you rotate something and a diffusion happens, and you in 5 seconds, and you don't like it, and then you kind of rotate it again, wait for 5 seconds. And this is where the 3D happens. Right?
Then I can rotate it to whatever viewpoint I want. I can also make it look more perspective or more orthographic.
So this is changing the camera FOV. And then finally you place it.
What we do is all the blurriness and missing details. No worries. We've got that covered with another button called upscale. You see, the 3D shape here is just a proxy of the actual asset. So I can use the proxy to find the best viewpoint. After I'm happy with the viewpoint, I can use the upscale button to restore the full resolution and all the fine details.
Wow. So what happens now is that this is the last step. Once you had the 3D in your scene, and you finish the preview stage, this is where the diffusion model then comes in and fix all the pixels to make it look perfect and harmonized. And so there is like more examples in this video, and I'll just stop here. I think you get my point. This same tech has been applied also to vector, and but the vector side, there's no, like it's actually a single diffusion model. It doesn't have any intermediate 3D yet. So there's actually no continuous rotation. And so like one step to actually do the same thing for the vector in order to allow this really free form positioning, rotation, etc., is to actually have a 3D. So yeah. And as you see, the key here, why user like it, is that there's no 3D in the name. There's no mesh. There's no it just looks like an image at all time, and this is the entry point for a lot of people these days.
You might recognize our.
And then, so how does it work? Let me break it down. So first of all, like as just similar to the tombstone, now we have a dog, right? Given this dog, first there's a diffusion model that generates these multi-view from a single input image. And this is, you can consider it to be actually a tiny baby version, a fine-tuned version, maybe of a video model, so that it has multi-view consistency. And then with that, you now sort of lift all this view up to a 3D Gaussian asset. And this is sort of what I've been working in Adobe. And then you can see all the streak of the Gaussian present there, and so it shows like it's still a Gaussian, and you can then rotate it right to the position you want. And once you fix the view, you run a diffusion model based on this current view and the original to get the final pixel, hopefully pixel perfect model. And then you can even run harmonization, etc. Yeah, so of course you can keep adding, improving this conditional upscaling, because here you can see already some problem issues with this conditional model, since it doesn't, the original texture it's getting is from this user input image. And the conditional model usually sees a smaller version of my Gaussian rendering, because the Gaussian usually it has some Gaussian streaky artifact that we actually want to remove. So the conditional model sees a smaller version of it to make sure these things are removed. And then it runs this upscaling. And in this case, since it didn't, in the original image, it didn't see the backside, and depending on the training data preparation, this side rather looks a little sheepy instead of a dog fur. Yeah, depending on asset, it works better or worse. But this is, you can see what I want to point out is the middle part, the how the 3D is being this intermediate fast responsive media for people to kind of play. And the tech behind the second part is a prior paper, I think it's in 2020.
There seems to be two questions here. Okay, can we go to the previous slide?
Yeah. Oops.
So from just the input image, it seems like there are multiple options for what the minion thing is, right? It could be a fluffy thing, or it could have been like a thin, flat piece. So is the first model where you get the multi-view images, is that stochastic to capture that distribution?
Yeah, that's a diffusion model. It's a diffusion model, usually fine-tuned from maybe a video diffusion or something like that. Definitely it's a generative model with the stochastic.
Okay, thanks.
Hey, Ethan. Can you hear me okay?
Yeah.
Sounds like great. I wondered, in this pipeline, there are sort of two 3Ds as hidden steps. There's the Gaussian representation, which is hidden from the user, but then there's the initial single to multi-viewed generation step, which also has in it some hidden 3D. And so I wanted to ask if that first step is just a crutch because we don't know how to go like straight to the Gaussians from the single image, or is there something more important about that first hidden 3D step to get the multi-view data?
That is a great question. I think there is, like, because I guess to already by now there is so many work like Meshi that does directly generation on the image, right? So you can say that, oh, why don't we go from here to here? I think that's your question.
That is my question, yes.
So I think so even now, I think I would say both ends I see pros and cons. For this approach that we adopted here, start from the assumption that we have way more videos and way more images out there. So the priors that are embedded in this diffusion model in the first step is potentially more general. And potentially I think actually people tried adapting either a multi-view diffusion model trained only on multi-view image to like new content, new types of content, like or if you train on static image, can you train it on, let's say, maybe scenes or humans, or sort of domain adaptation in terms of content. And another is trying domain adaptation from diffusion model, like train just on images, but try to have the multi-view consistency. In these two ways of fine-tuning, apparently it is much easier to actually force the model to learn force a general diffusion, image diffusion model trained on all type of object and scenes and all the images out there, and force them to have 3D consistency. And so that was the observation and the consideration that, okay, since it's much harder to get human 3D data, and directly training an image to 3D will probably perform not so well when your user data is out of domain, out of training data domain, such as a human. Since you have so little of such data, so hard to get. I think I still see this with the top performing 3D generation models out there, such as, I think we tried Trellis on human faces and just entirely collapsed. And on, I think Meshi is getting great this year with their last update with human, but in the past it has been not. And so this, I think, I don't know whether so far this answered your question. Is mainly like which way to adapt to be more general. And I think our conclusion is this way was, for us at the time, definitely more general and more sort of maybe it generalized better.
Perfect, thank you very much.
Welcome, that was a great question. Okay, any more questions to this slide? Or okay, so I was going to like give a little context of how this lifting works, because we'll talk about it later. Yeah. So how it works is actually a sort of feed-forward model without any statistics involved, actually. So this model takes different posed images and they patchify it, and then it runs a full attention like patch to patch, cross view transformer block, and then predicts for every pixel a Gaussian in 3D. So you can imagine there's a lot of Gaussian if you have a lot of inputs. And then these Gaussians are merged, and you train in such a way that the Gaussian looks good in different viewpoints, in viewpoints that are not seen in your input images. So yeah, this model is the backbone, and we'll come back to, we'll use it later in the next work. Okay, any questions to this model? If not, then
Hi, sorry, I didn't totally understand how the model works. So, when it's generating the per pixel Gaussians, is it doing it? If it's doing it per view, does it know all of the views?
yeah. So basically, we want every because this block, the transformer block, you see my mouse, right? Do you see my mouse? Like
Yeah.
Yes.
This transformer block in the middle, every attention block sees across all the views and all the poses of the view. So you should know, like just from the architecture step, you should know about all the views. But at prediction step, every single image that we put in actually predict per at its pixel its own Gaussian. You can think if you know about VGGT or works like that, it kind of works similarly, right? You have a bunch of images, but like the middle, the block in between, like know of all the images and if they're given pose, or in VGGT they don't even know the pose. But then per image, it predicts its own individual prediction. Like in VGGT steps, and here is actually I would say it's basically like VGGT, but trained for predicting depth and Gaussian parameters, and on the object scale. This is how I see this model in its core. It's trying to predict per image depth through a bunch of post images, and each image depth is actually a point in 3D, but it's also associated with Gaussian parameters. And the loss is trained with the rendering loss to make sure the Gaussians look correct on different viewpoints. So far, so good?
Yeah.
Okay. Then let's move on. So why does this work? As I hinted,
I wasn't sure you were going to move on from that project yet. I wanted to ask a question about the super resolution step. You showed the example of the dog with the fur on the other side that looked like sheep fur. If the goal is to make sure that the appearance of the upscaled high quality output looks like the appearance of the input, have you tried something as simple as just patch match, or a newer perhaps neural variant thereof? Because it seems like what you really want to do is steal patches from the input image rather than try to hallucinate them completely from.
Yeah. We haven't tried. So this example, I would say it's a bad example. In reality, it works much better. And the reason it's bad is because there are not so many data that we have has such furry texture. And for a patch match kind of example, sometimes, so here there's a lot of repetitive texture. There are other, you can imagine maybe if you take a shot at a human face, just me now, if I have my hair tied and then you kind of rotate it back, you will see a lot of hair, and that hair may not find the correct patch from the start, from the front view. So I think that's a good point for the touch. Like it could be a good fix for specific data. And yeah, in general, this is probably a not so flattering example of what we have worked on. I like the dog. Like, okay, I'm gonna put it out there.
I was just thinking it would be interesting if you had some kind of neural renderer that could be conditioned on an input image and could have some sort of confidence about when it knew what regions it could borrow patches from the input and when it needed to just hallucinate them completely.
Yeah.
Yeah.
Yeah. And also, yeah, I want to say that we are adding already internally working on, there is a better version that actually considers other views in this conditional upsampling, and it solves this problem specifically. Yeah, and perhaps the next one
Hi, Yifan. I had one more
We
question.
have more questions for you.
Should we pause on the questions, or like what would you prefer?
So what time is it? We have 20 minutes left. Let me maybe go to the next project. What do you think?
All right. Yeah, sounds good.
It's actually, I have more like technical part. I mean, there may be even more questions.
All
Okay.
right. Sounds
Yeah, I just so that I like let's jump directly to the next project. We're putting this paper out, and it's actually an internship project that happened this year. Aditya worked with with Yang and Aditya sitting next to each other, so he knows a bit of the work already. Let me tell you what the key motivation is. So let's say you have this. The key motivation here, like hinted a little bit, is that okay, so we have this 3D and it's kind of transient for now because once you like fix the view, you render it, we kind of just like assume we can forget about it. But what if the user actually want to do something to it, like edit it? And what we want is really also like very fast mechanism to give direct feedback of what the edit will look like. The edit should be persistent, view consistent after you edit. This would have been so easy on Mesh because you just paint on Mesh, but not so much on Gaussians, right? And but we still want to keep the Gaussians because it looks really nice, better than Mesh in a lot of rendering, like these fur-like fuzzy like structures. So the goal here is how do we edit Gaussians just from image editing, and how to propagate it efficiently to the Gaussian such that it can be 3D consistent. Okay, so how do people do this? There are mainly two types of approaches, and one is doing multi-view diffusion, like of the first stage of the prior work I just showed. You do some editing and you propagate that edit by fine-tune maybe a diffusion, image editing a diffusion model, or video editing a diffusion model, and you kind of propagate that across the view. And then you run the same reconstruction again, and then basically you get the result, the same result. It's like only the first stage change. The problem with this approach is that there is always loss through either the diffusion process itself or the lifting process. Here, you can see that the original quality, even though like, it's already not great, but you see that the input, it just slight drift. Here, I think what they're changing is the ear, right? But then you see, okay, the color and the detail of the horn, all of the hair, it changed. It changed at what stage? Both at the diffusion and the lifting stage. So another approach is that, okay, you can still do, the editing. There are different mechanisms to do the editing, either through this just like one diffusion pipeline, or I think this interactive diffusion stages, like many people also like change one view, edit one view, and then iteratively, so they change one view, right? And then they keep reconstructing the scene, and in the loop, they update the data by changing another view, and then it kind of with the schedule, it fuses all the data and iteratively update the with the data changed, you can then reconstruct the 3D scene entirely just through optimization, like Gaussian optimization. This usually gives a better quality, but the problem is that it's so slow. It's just not it's not plausible to incorporate in a working flow, in a workflow that you can really apply. So now the two objective is that it has to be fast. So it's a feedforward model that we're trying to do. And then the next ingredients is how do you not destroy what has been already done? either in the generation itself or in every edit, can the state of the edit be preserved? And so there are these, the second one correspond to a technique or a paper that I'll explain. It's a prior work, but here I'll go through like what is the intuition and construction of that. So let's jump directly to the test time training part. How do you memorize the state? The state or / the context is something that correspond to actually previously recurrent neural network, right? Because you have inputs and then it generates, the recurrent neural networks give you a state, and then it basically takes the state updates with a new input, and gradually the state evolves to something that is the state evolves to something that captures hopefully every input you have given, and then the output is what you want. However, I think LSTM has never reached a really matched attention. In an attention model, you will have the state is like every token, or well, attend to every other token that you have. The state is like attend to everyone. So it's you don't in a way the state is a quadratic, it's a matrix. It's a quadratic, or it can be an upper lower triangle matrix, and it has way more power than just a linear vector state in the RNN model. And that's where I think the transformer basically being so much more powerful, RNN slightly faded out. And what TTT does is that instead of a passive vector that just remembers a single vector that remembers a state, now the state is actually updatable at inference time, updatable weight. It's like a small internal network. Don't worry, I'll have a more visual slide in later. But here, just to say that there are two stages. One is that there's an outer loop that when basically outer loop, well, given a new input, we will the new input will generate will basically generate the context for the current new input, and then there's an inner loop that updates the weights that aligns with this input. So this stage is called adaptation or update of weights. And then once the weights is updated, you can apply to the current context. And so here is a better slide of how this is done. So there's like 5 or 4 equations. Let me just go over them one by one, so you know which is outer loop, which is inner loop. So the first one, projection, happens in the normal training. Normal training outer loop, and inference also outer loop. The theta is what we are used to in a neural network. What they call in TTT is called a slow weight. It's when we update during the training. So given a new input xt, the theta we're training in the slow weights will give you a set of parameters to give you the key value and query, just the normal thing. And then with that, now the key part is the middle two. With that key and value, you now update the weights that are actually adaptable for this inner model. And the weights are called fast weight. So how you update it is that as proposed in the original TTT paper, you simply update to match the key and value, and this you optimize it to get a new set of weights. So the new set of weights is optimizing this or minimizing this above loss. And this update rule, this minimization can be done in many smaller loops inside one training pass. one training forward pass. And then with this updated weights, you apply to the query that you obtained earlier on with your slow weight. This may be confusing, but let's look at this diagram. You have this. So now instead of a transformer self-attention block, you have now this TTT block, which takes the new input, projected. This first step is the slow weight. It happens all the time, right? You have the K, V, and Q query. With these, you apply these two equations, and you update the weights to get the new weight. And then the new weight gives you basically a smaller network that you can then apply to get the new output, the ZT. So these as a whole, it will replace the original LSTM's state vector. Yeah, I am sure you have questions. Maybe for the sake of time, we just go through to the next slide. What do you think?
Sure.
Okay, so maybe here helps as well. So what is now, so originally it's proposed like that, right? And the problem is, so not a problem, but it didn't scale well, it didn't catch up. So another work at Adobe this year is actually made it work on novel view synthesis and like large context reconstruction. Like on a video, you generate like novel view synthesis on a video. And what they changed is that they pretty much changed this inner network to be something slightly more involved. Instead of just a linear model as the inner model, they changed it to be MLP. And because of that, the update of the minimization of the L that I showed earlier is no longer closed form. So then they applied several. So the update is then a several step update that is based on gradient descent with an optimizer called muon. So this is so we are now using this later one, and every training step you will have 5 optimization happening to get this W, and your training backward will update the projection weight. So at inference time, your projection weight is fixed, but you still do this update to get the new weights, and the new weights are the update in natural language. It simply means inner model, so that with weights adapted to fit the current XT. Okay.
I have a question, Yifan. At training time, how do you get training data in the form of a sequence of edits like this, or a sequence of XTs for your context? Where does that come from?
You don't need to get a sequence of individual edit, so you can just have a before and after edit, and like maybe one edit, and then so every XT maybe correspond to an image patch or one view of that edit. That's nice. So XT, the T is not what time for edit, it's simply a token corresponding to the current edit. So what the data we got there, so one trick data we had is actually simply because we render the image in higher resolution, you can create a refinement editing by downsampling your high resolution rendering. And so that's a trick. And then another one is we kind of just painted graffiti like random paints over the texture and render them out.
Got it. So you have to be able to create before and after pairs, at least at training time.
Yes.
Or different edits you want to.
Yeah. Okay, so how now, before in the original TTT and the language time TTT, they're all updating this token correspond either to words or to pixels. Here we get pixels, but we're trying to update voxels / Gaussians. And why I say voxels, I'll hint later. So there's like different updating. We update the weights, but we need to apply to another modality. And so that's why, so the new image come in, and now we add this lower part, which uses the same weights to update, instead of just the image tokens, we also update the Gaussian tokens. So where do these Gaussian tokens come from? They come from the original Gaussian, but the problem is there's a missing piece. That this original Gaussian, if we just use the raw Gaussians directly, it will just not work in practice because there's just so many Gaussians. There sometimes over 500K and not feasible to train. So all the things that from now on, I'm going to like say, so we have this TTT piece, I think that's central for this editing case, but everything else is basically assisting how this can be done in an efficient and just how it can be even realized in PyTorch with modern GPU. So there's so many, so we need to compress it. There's a lot of, especially as you can see, the compression costs almost no PSNR. So there's too much redundancy in our original raw Gaussians. So and also like every Gaussian is just individual Gaussian tokens, and they don't say much things about, what is the relationship maybe with the same color Gaussian in my neighborhood, or, same color Gaussian maybe in the backside of the dog. So the Gaussian token or the feature themselves have no context. So what we do is that we take the original 3D Gaussians and we actually pass through the same GSRLM. We render them out, by the way, in different views and pass the original GSRLM. And the GSRLM basically, because it produces the Gaussians through this cross-view attention, it has context. And we keep that context. So that context tokens actually enhance the original Gaussian attributes. And then the second important part is that we have this another neural network based on actually voxelized groups of Gaussians to make sure that we can compress it. And how we do it is basically we construct these voxels of on the fly based on where Gaussians lie, and the voxel is a simple you just kind of do a discretization. So it's constructed very fast, and then so here in every voxel there are a variable number of Gaussians in. But at some stage, there is a cross attention that takes only the most visible Gaussians in terms of their opacity to query. So after this cross attention block, because your query token is much less than the original incoming, let's say here's okay, symbolically here's 4, but you query only 2. So every voxel after this cross attention only gets, the number is reduced to exactly how many you query. So this block is trained, so this part is fixed, and we train this block by itself to make sure the reconstruction is lossless. And as you see earlier on, it is indeed lossless. So there is when you see there is a slight PSNR, it remains the same as in general, on average, it remains almost same as before. And actually SSIM and LPIPs is actually improved. But there's significant reduction in Gaussians. And this is important for the TTT training to even work. And so here after the stage, you get the same like visually the same Gaussian assets, but much more compressed. And then what you do is that you put these new Gaussians into together with the tokens that we extracted through the first GSRLM stage into the TTT block that I explained earlier. So this is the model architecture. And now I want to show some results. Do you see a page with maybe I don't think you're seeing. Let me just share it again.
We can see it.
Yeah, so like I want to show some examples. Okay, so this is the original GS, and we show there's different ways you can, depending on the data, same model, same architecture, you can apply to different applications. So the same one is what I said is, you can create this refinement editing by just downsampling your training to training rendering and keeping the original rendering like as a pair. So like this is the original GS, and after refinement, we get, so this is the new user input view, let's say. So after refinement, it looks much closer. And by the way, we're showing a different view so that you know that this is view consistent. And then you can also paint. Okay, you just kind of draw over something and it doesn't look actually natural at all. But then when you render them, they look kind of okay. So this is a video. Can see that there is here that the projection, there's not so perfect at the R part. It kind of follows the follows the curve. But what I find most interesting is that this global edit with the relighting, because basically we're giving just these. Actually, it's interesting to show them maybe here, right? So like the original GS and relit, and with just one view, one input view, it kind of infers what is the back, even though the reconstruction model should theoretically just update what it has seen. But because in the training we are supervising not only on the provided edit view, but also on the global view. So we kind of learned to associate different Gaussians and update them coherently. I think this is important. This is feasible because it carries these tokens, enhanced tokens that have some context. And I want to, like, for this point, I want to go back to well. I want to get back to the slides where you see this view, and I think it's very interesting. So here, this is the input Gaussians, and what we want is that we want to change the colors. So okay, the input Gaussians are showing the three views, and the arrow map shows how far it is to the ground truth under different lighting. And now we provide after providing the relit. Let's say the user like rotated this figure, right? They chose this figure and changed the color, changed the lighting. And you see that, okay, because the back is like what you see got dark, right? And then, but you don't see the front getting brighter. However, this view, the front view after this one update did entirely got brighter. And I think this is what I was alluding to, that it got, some global context. And then with every new edit update, you can provide multi-view edit, like this iterative one, and the arrow map just keeps on reducing. And so this is sort of what I mean by that it remembers the state of the edit, and it can be persistent. So yeah, maybe here I also just want to highlight why is it important to have the feedforward setting, because you could think of for certain applications, not like the relighting, right? The relighting requires some, I think it's harder to, so first you can use optimization. If you have enough view, you can think of just generating a bunch of views and then optimize the Gaussians, like the traditional 3D Gaussian optimization. For some edit like relighting or graffiti, it's not possible to actually regenerate a lot of views. And so, but for certain like application like refinement, you can, right? Okay, so let's just focus on these refinement tasks and see how this optimization method performs. And they perform actually quite okay. Like if you compare the visual effect, especially just the like simple Gaussian optimization, they look great compared to like similar to ours. But they just take 5 to 8 minutes. But with the feedforward model, it takes 1.5 second for the first stage with the compression done. It takes 1.5 and it needs to be done once. And then later on, every single TTT update is around 0.3 per update. And this is huge because that's the unblocker that allows a user to actually use something like this. Okay, I think actually that's the most of what I want to show. And I want to like say a little bit about the future work. First of all, in the data, we didn't have any geometry changes. So like one thing to add is, okay, yes.
Yeah, it seems like we're running close to the time, so it'd be nice to wrap up soon.
Okay, so future work, after future work, we're kind
Oh,
of
we're able to go, obviously go.
Okay, so I want to say that another is, how do we enable scene scale editing? And for that, we probably need a better, more efficient structure. Now it's, this voxel grid, but then we can have a multi-scale voxel, a multi-scale grid like off tree and that kind of structure. Okay, so this is like, what if I, want to draw, a new geometry? Can I? Currently, the model doesn't allow it. Conclusion, very quickly. Here's what I think now. Is 3D dead? I don't think so. But this manual modeling is dying. I think there are very few expert 3D artists now that actually still they're great. I don't want to say that they're awesome, but there are fewer and fewer people use them. Use hardcore 3D modeling, and of course, if there's something simpler, people gravitate towards simpler modeling. So what we can really do as 3D researchers is to in the realm of GenAI represent things that are directly in 3D, such that with a vision to enable responsive and consistent content. So like I think that is how, exactly how that's how I would now look or encourage 3D researchers to look for angles and directions in publishing papers, also in industry, to how to pitch like what 3D can be used. So like instead of building or just reconstructing, building interfaces that can align the GenAI or workflow that works well with leverage the 3D, the benefits of 3D, such as real-time control, etc. That's
right.
my.
Thank you so much for the talk, Ifan. I'd like to just thank everyone for the talk. Yeah. I'm sorry about the fact that we took like 5-7 minutes in the start for just the AV, but yeah, thank you so much.